Hey, can you hear me back there? Yeah, my voice tends to drop a lot. So I just want to welcome you all and spend a couple of minutes just talking about the Peter Sinclair lectures and to introduce our speaker, but I won't take up much of your time because I want to give David all the time that we have. So as most of you know, the Peter Sinclair lectures were set up in 2020, soon after Peter's death from as one of the early victims of COVID in March 2020. Peter was professor in the department here from 1994 until 2020. So it was a great and untimely loss, but we that we have that we host. We also have an undergraduate prize named after him, an MA prize named after him, and he left us a small bequest for to fund travel for PhD students, which is also named after him. So we remember him in many ways, and this is one of the main ways. We started in 2020. Our first lecture was Tim Harford, who used to be his student at Brasenose. We've had Tim Harford, Dan Coyle, uh, David Ramsden, Joe Stiglitz, Charles Goodhart. We've had a number of very eminent lectures, and David is going to be our 11th eminent Peter Sinclair lecturer, our third in-person lecturer. The previous two people were Wendy Carlin and John Milbar, who were after COVID restrictions were lifted. They were the first three in-person speakers. So it's a great pleasure, the greatest of pleasures and honors to introduce David Hendry to you, my friend, mentor, co-author, colleague, um, and someone who's had an enormous influence in my life from the time I was a starstruck grad student to now when I'm old but not so wise head of department. So I'm very it's a great pleasure to introduce you to him. He has too many honors to mention. Only one knighthood. Um, the the um, the membership of almost all the distinguished academies of science and scholarship, several awards, honorary doctorates. You can look him up, and you will see all this. It wouldn't be an understatement to say, I think, that he is one of the most well-known and cited econometricians in the whole world, and it is lovely to have him here with us talking about the Anthropocene. So without any further delay, I give you the floor, David Hendry. So about 50 minutes for you.
Thank you, in India, for that very generous introduction. It's a pleasure to be here. Thank you all for coming. I was quite a close friend of Peter Sinclair's when he was in Oxford for the many years at Brasenose. And he was a wonderful colleague. He's the sort of person that research assessment exercises just don't take into account what their enormous role is within the department. He was a fund of knowledge, a wonderful colleague, always willing to advise and what to read in vast literatures. He'd say, oh, ignore all of that, but read this particular paper. And from his encyclopedic knowledge, which really, before you could look him up on the internet, you had to go to a library to find things. And that could take you all day to find one or two bits, and just ask Peter and you'd get it immediately. He was indirectly interested in climate change, published on the impacts of technological progress and jobs, which will be a key issue in the green transition, and the optimal path for taxis and fossil fuels, which is already quite an important issue. He married Jane Hendry something like 10 years ago and rekindled his interest in climate change. He was very much an environmentalist, and we've interacted a couple of times both in Oxford and King's Lynn discussing many climate-related environmental issues, including damming the Wash, for example, to get enough fresh water in 20 years' time when climate has changed too much to leave the southeast coast desiccated. But she also modelled bird species threatened with extinction and looked at coastal erosion. Funnily enough, my last interaction with Peter was November 2019, not long before he was caught by COVID, when I delivered the Lee Sigouin lecture here on climate change in the long run. Today, there'll be a little bit of the long run, but I'm much more concerned with what now. So as a summary, for those of you who want to fly off, evidence from 500 million years provides a stark warning. The only reason for mass extinctions in the past has been climate change, not the climate level. We've had hot houses, we've had cold houses, we've had ice houses, but the change from one state to another is what causes mass extinctions. We're the last trigger. All the previous ones have been natural. This one is as in India called it, anthropogene. We're increasing levels of atmospheric greenhouse gases. That's leading to worldwide temperatures slowly rising in a very varying trend. And that in turn is raising sea levels, causing more droughts, floods, hurricanes, wildfires. It's affecting nature, obviously, from the changes in temperature and rainfall. It's affecting biodiversity, and it's beginning to affect economies. For example, the latest floods and hurricanes have caused considerable damage in many countries. I'm going to use the ancient framework of earth, air, fire, and water as 4 essential ingredients for life. Now, the Zoroastrians got this right. They understood you couldn't live without earth, or air, or fire, or water. Poor old Aristotle got it completely wrong, thinking they were the basic constituents of life. But that obviously is not the case. But we'll explore climate change looking at the role of all 4 of them and what actions humanity can take to avoid disaster. Because adaptation isn't meaningful if food, water, and land resources are inadequate. Yet most mitigation steps will actually be beneficial. I hear people talking about the costs of climate change. Completely wrong. The investments needed to do climate change and the benefits that we'll get from those investments rather than continuing to invest the same amounts in greenhouse gas providers. We're going to propose 5 sensitive intervention points, SIPs as we're going to call them, to chart a route to near net zero greenhouse gases for Britain by 2050. And there's been recent work by my group on evidence of what policies actually have achieved climate improvements. So this is the layout. Can humanity really change the planetary climate? Yes, it can, very, very easily, much more easily than the average person seems to realize. Then earth, air, fire, and water, 500 million years of mass extinctions, 800,000 years of ice ages, and the atmospheric CO2 debate, was it causative or was it a response? Then the Industrial Revolution and its impacts, modeling UK CO2 emissions, and then what can be done in the future, and the odd conclusion. So a bit of background. The climate clearly depends on the energy balance between the sun's incoming energy and re-radiation. So that depends on a huge number of factors. But one of the most important is atmospheric greenhouse gases, like water vapor, carbon dioxide, and others we'll discuss later, which are crucial in retaining heat. Too depleted and the planet cools, once being a snowball, with glaciation even in Death Valley, the hottest place going. Whereas excessive greenhouse gases lead to very warm periods, the Eocene about 50 million years ago, which then lead to very high sea levels and very much smaller land masses. And remember, we have a gigantic human population of 8 billion plus people. Past climate change has been driven by natural forces, mainly plate tectonics, volcanism, magnetic pole switches, and the orbital variations the planet goes through naturally. And life has survived great changes and thrived in completely different temperatures. But en route, it's the number of species that went extinct. And that's what's going to be the real threat over the next 100 years. If we lose all the pollinators, for example, we're in deep, deep trouble producing food. But in any case, the world has got to be shared by us, not just focused on us. Even if 1,000,000 years later, there's lots of other species around once we've gone. So change is the key word. Humanity is now changing the climate by vast emissions of greenhouse gases, mainly CO2 from burning fossil fuels, but quite a number of others. So this is climate change and CO2 over the 800,000 years of 8 major ice ages. I think this is okay. The amount of CO2 in the atmosphere is 25 parts per million, ppms, as they're noted. And there have been 8 major ice ages coming and going, starting with the belief by Brunhes that it was caused by a magnetic transformation between the South Pole and the North Pole that left a period of the Earth being unprotected and developing ice ages. There's a mid-Brunhes transition that's still not well understood, where the variability changes, and you can probably see that by the eye. Supervolcanoes like Taupo in New Zealand have a huge impact, relatively speaking, but what have we done? This is what we've done. In 250 years, we've dwarfed the 800,000 years of ice ages. We have put up 130 parts per million relative to where we started in a quarter of 1,000 years. And 1 part per million is 7,800 billion kilograms of CO2. We're altering the atmosphere and hence the climate. And we can see these alterations. That's the recent measures taken by Keeling in Mauna Loa using flask measurements, which are extremely accurate. It's monthly data in this particular graph. The bottom line is what the trend was between 1960 and approximately 1980. The middle trend that you see there is the average of the whole period, and you can see that the current trend is way above it. Despite all the COPs, Paris, etc., we are still accelerating our production of greenhouse gases, not just slowing it down, not just stabilizing it, but accelerating it still. And this is having huge effects, particularly on the poles. I've only recorded the Arctic temperature. And you can see that one of the features of economics that I've emphasized throughout my career are breaks. The trends leap around. They start off, they go negative, they jump up for the Arctic, they change very much, but dwarfed by the Arctic effect for the world as a whole. And if we look at the ocean heat content, the oceans play the major role in stabilizing our climate, in absorbing the excess heat and absorbing the excess greenhouse gases. And you can see the change in trend in ocean heat is quite dramatic, and it's speeding away now in terms of gigantic volumes of heat accumulating in the oceans. That's got to go somewhere. It keeps going until it equilibrates with atmospheric temperature, but once it reaches too high a level, it starts to give out heat. So beware. And this is what happens to global sea level. Again, it's risen dramatically compared to what was happening in the 19th century. And you can see at the very end of the graph, the top right-hand corner of the graph, it's already exceeding the latest trend. So these are the sources of radiative forcing. Radiative forcing is the amount extra that's being pumped into the system. And it's made up of the components of natural forcings. And you can see the wonderful jobs the volcanoes do in lowering the temperature, but for very short periods. And we have papers on how to detect those effects. And so do other scientists, of course. The green line is the aerosol forcings. These are pumping out pieces into the atmosphere that block sunlight and lower the temperature. And that's turning around. And you see that in terms of the red line getting close to the green line, the blue line. That now the radiative forcing isn't just CO2, it's the reductions in the other blocking ones. So Earth, air, fire, and water. Let's start with Earth. It's a placeholder for our planet's land. It's both living space, soil for agriculture, forests, wild areas. Continents and topography have shaped by plate tectonics and volcanoes over time, and both affect climate and play key roles in mass extinctions. So climate change currently is affecting land flooding. Think of Pakistan, think of Spain, think of northern Germany. Rivers in the sky can hold more water than the entire Mississippi Valley. the Mississippi River. And if that dumps itself in a day on where you're living, you are flooded to great depths that will kill people and destroy properties of various kinds. Also, when it goes away, it sweeps off soil, so we get a loss of soil. But also climate change is increasing droughts. We get much longer droughts in some areas, particularly Europe suffering about a decade-long drought relative to its past, and that leads to loss of crops. It leads to dust storms, wildfires, which have been happening everywhere and been in the news, and potential tipping points for tundra melting, which would raise the world's temperature very rapidly in a very short period of time. Now, getting our food takes roughly 40% of the planet's land area, about 50 million square kilometres. For the UK, it's about 56% is farmed, 35% is natural, 6% is built on. I hear people wittering on, the whole country's covered with houses and buildings, etc. It's 6% of the land is covered with any form of human construction, including airports, roads, houses, etc. And that's 200 meters squared per capita. That's it. That's all we occupy. Okay, maybe there's far too many of us, but that's a different problem from us having too many houses. Much of Britain is still green, including green urban area. But it turns out that crops are being grown mainly by artificial fertilizer and farmland created by deforestation, plus animal husbandry, mainly cattle and sheep. And they all lead to greenhouse gas emissions. And sea level rises obviously cause coastal flooding and reduce usable land areas. Now, our air, people misunderstand that atmosphere is no thicker around the planet than a sheet of paper round a soccer ball, football. That's how thick it is. You look at this graph taken from a satellite, you can see the planet is huge and the atmosphere is tiny. Can we change the atmosphere? You bet we can. There's very little of it. Get to the top of Everest, you can't breathe anymore. There's no oxygen left. That 78% of the atmosphere is nitrogen, 21% oxygen, though it's changed a little bit. Water vapor is 4%, and there's a little bit of carbon dioxide, about 450 parts per million, nitrous oxide, methane, ozone, and some noble gases. And they're all changing the atmosphere. Nitrous oxide from catalytic converters and nitrogen and phosphate from fertilizer have doubled in the last 50 years, and now about 7% of greenhouse gas emissions. And it's 300 times more potent than CO2, so it actually might be making a bigger impact than people realize. Atmospheric methane has doubled the level we've ever seen over the past 800,000 years. It's about 20 times as powerful as CO2, but it only hangs around the upper atmosphere about 15 years, getting converted to CO2. Current estimates, though, of methane hydrates, they are crystal forms that embed methane in low temperatures, high pressures. There's over 6 trillion tons of it estimated to be in our planet, which is roughly twice the CO2 in all fossil fuels. And if we heat the oceans too greatly, it'll melt it. And that will cause temperature changes of up to, 10, 12 degrees in short periods of time. Now, atmospheric gases have changed greatly over deep time, especially from volcanism giving out CO2 and the exchange of CO2 for oxygen by photosynthesis, which has led to some great extinctions by cooling the planet dramatically. You do need CO2 in the atmosphere. You just don't need the levels we've currently got. So atmospheric blanket's essential to life, but long wave radiation light comes straight through, but when it goes back up again, it gets re-radiated. It's responsible for the greenhouse effect. We don't want to end up like either Mars or Venus. Thank you very much. The fire will be the placeholder for energy, presently from burning fossil fuels, and that's putting the on a lower CO2 levels in perspective relative to the 800,000 years of ice ages. There's hope for renewable energy, and it comes from all four. Earth can give us thermal energy, air can give us wind energy, fire can give us sunlight, water can give us hydro and tides. And the result's been a dramatic rise in monthly air temperatures by decade. So we start off with the 1980s, 1990s, 2000s, and as it goes up, you can see the rise in temperature. It's way going to be outside 1.5, and it may soon be outside 2. So Paris just looks like a joke rather than a serious thing. And every month you find a record. The record January 2025 is the highest recorded by humanity. What about water? Surely we've got lots of water. Can't do anything about that. We have not. Water is tiny. It's a big puddle on the planet. People are fooled by this being a blue planet because of the huge, wide oceans, the ice sheets, the glaciers, the lakes, the rivers. You put it all together, that big blue ball, 860 miles in diameter, is every form of water on the planet. Can you heat that? Of course you can. Can you pollute it? Of course you can. Can you fill it with plastic waste? Can you turn it to weak carbonic acid? Dead easy. The oceans are not our savior. They're something we desperately need to protect. The little blue dot beside it is all the fresh water on the planet. And just below the little blue dot is an absolutely tiny blue dot, which is all the drinking water on the planet. That's how little there is. We need to be very, very careful of our water resources. And humanity is not paying much attention to them. Now, because there's so little ocean, it's very easy to heat it. And the sea surface temperature jumped suddenly in 2023, 2024. That's the yellow line, way above all the other lines, but it has been rising steadily. And when it gets to certain levels, various sea life forms die. Coral's the one you probably know about, but many, many forms die. And it's the basis of life. You kill off all the sea life, you're going to kill off all the bird life, you're going to kill off much of the mammal life, and you're going to kill off us in big numbers. So we have a real worry from my viewpoint of what's happened in the past and what it tells us about what's going on. Now, where did these 500 million years of mass extinctions come in? It came in at the major, what you might call boundaries between the different stone forms of Ordovician, Devonian, Permian, Triassic. The one everyone knows about is the Permian Cretaceous, the Triassic TC boundary, when the dinosaurs went extinct because of a possibly, well, we certainly got hit by a major meteorite, which did a lot of damage, but it's also possibly due to India, which was scraping over the ocean floor, heading up to crash into Asia. And as it did so, it released gigantic quantities of CO2. And it also formed vast volcanism in the Deccan Traps, which are 300,000 cubic kilometers of basalt, right? Just absolutely gigantic. And that's one of the drivers. But the others are all due to major changes. And that's the percent of species vanishing. And they're all due to climate change. I'm going to miss this slide given time. So let's look at the last 800,000 years of ice ages and atmospheric CO2, because I've learned much of what I know about climate before starting studying this. But the first study we did were ice ages, where we had 800,000 years of data, where there was a big debate. Were the ice age transitions caused by CO2 in the atmosphere, or were the transitions causing CO2 in the atmosphere? And can you tell which is which? Because the ice age data, taking an enormous effort by paleoclimatologists to collect, but it's at 1,000-year intervals, and 1,000 years is a very long time for things to happen in, but it's very short relative to the Earth's orbit around the sun and the tilt of the Earth, etc. So the Great Ice Age, as he thought it was discovered by Louis Agassiz in 1840, because he'd seen the movements of glaciers in his native New Zealand, Switzerland, and he'd seen that they moved huge stones. And often people were puzzled by stones that had moved 150 miles from where they'd originated. How did they get there? Who are these people dragging these stones? We know they can do it from Stonehenge, but it seemed unlikely that they just dragged a stone and dumped it in some unusual place. But Archibald Geikie found plant fragments between layers of glacial deposits. So there must have been warm periods and many glaciations. And the calculations, for those of you who are worried about your future, were done by a guy called James Krall, of whom you've never heard, I suspect. He worked out why ice ages occur, and he drew a timeline, and he's these absolutely wonderful fold-out graphs that you can get in his book in the Royal Society of Edinburgh's headquarters, looking at them, showing all the ice ages theoretically worked out by him. Now, he was a janitor in a school, cleaning blackboards. And he taught himself climatology from the little amount he got going to meetings at the Royal Society of Edinburgh and learning the mathematics from cleaning blackboards. Absolutely fantastic that people can do that back then. Now, his research was later amplified by Milutin Milankovitch, whose name now attaches to these kinds of things, calculating solar radiation at different latitudes from interacting changes of eccentricity, obliquity, and precession of the Earth. Milankovitch also corrected Kroll's assumption that winter minimum temperatures mattered in starting ice ages to show that low summer maxima were more important. It snows in winter, it's not warm enough in summer to melt it. It snows the next winter, not warm enough in summer to melt it. The snow builds up and eventually gets to a level that it's reflecting so much sunlight, the Earth cools and you get an ice age. And then it ends when various things happen. The Earth changes its position relative to the sun, or alternatively, you get lots of volcanism that turns things black and reflects and absorbs sunlight. So these are the global drivers. Eccentricity of the Earth has varied from 0 to about 5 degrees. It's not tremendously non-circular, but we're very lucky at the moment. We're in one of the very low elliptical orbits. So it's mainly circular, which allows the temperature in the Earth and the climate to be relatively stable. Likewise with obliquity, the Earth's not tilting more and more, less and less. It's tilting a reasonable amount, about 20-some degrees, and that's fine. It's the northern hemisphere facing the sun in winter and away in summer, whereas the southern hemisphere gets the opposite. So they have much colder winters and much hotter summers than they do in the northern hemisphere. Precession of the nodes, the wobble of the Earth, and that determines whether the obliquity is facing one way or the other at different times of the year. And then Milankovich's summertime solstice at 65 degrees, and you can see the very end of it is relatively quiet compared to some of the periods. Now, there are very close relationships between the ice age variables. If we want to work out what CO2 is doing, I've plotted the negative of the volume of ice against the variables, because that gets them positively correlated, whereas normally CO2 would give us less ice. And there are quite big differences. I don't know, the point here is does it show up there? No, it doesn't. No. Okay, if you look at the bottom left, the top left graph, CO2 and negative ice, you can see at the start there's very big departures, and later at about 600 and 450 years, there's big departures downwards and again upwards later. CO2 and temperature have differed even more at times, and that's important because these deviations give us a chance to test, is CO2 causing temperature or is temperature causing CO2? And temperature and the negative of ice are very highly correlated. But again, there are departures. Now, we don't know if these departures are measurement or real. I mean, this is measurement stuff 800,000 years ago from core drilling in ice. They could be either, but we're going to use them. And then the sea level and the amount of ice matter greatly. But again, there are departures that are quite surprising, especially at the beginning before 400,000 years ago. Very odd that the sea level was going up while ice was actually going up, but remember, it's a negative. So if ice ages are due to the orbital variations that Kroll and Milankovitch thought, why should CO2 levels correlate so closely with the negative of ice? Is it that that's what changes the temperature, temperature then changes ice, and CO2 is doing what it's currently doing in the Anthropocene? The answer is no, we don't think it's that at all. The oceans hold about 60 times more CO2s in the atmosphere, and the deep oceans, especially the Southern Ocean, act as a carbon sink during cold periods, and it releases it during warm sea periods. Think of setting out your glass of sparkling mineral water and coming back an hour later. It's no longer sparkling. So during cold periods, they get absorbed. Warm periods, they release it. And that looks as though it's the CO2 that's causing the warming. So orbital variations drive the temperature, that changes ice volumes, and that changes sea levels, but that feeds back to temperature because more CO2 in the atmosphere means a warmer world. So Jenny Castle and I modeled it, and then saved the last 100,000 years. If you've got 800,000 years of data, it's quite nice to save 100,000 years. And as an econometrician, to be able to forecast over 100,000 years, very exciting compared to the 2 days ahead or whatever we do in weather, or a couple of months in economics. And the answer is the model works that we estimated works extremely well until about 25,000 years ago, and then it distinctly goes off. We start 100,000 years ago, and so by 25,000 years ago, you can see all the red lines are deviating greatly from our predictions, assuming there's no extra climate change. So it does look as though climate change actually started happening about 25,000 years ago, something of that order, if you believe our kind of model. And the fact that it's now lying outside our confidence intervals for both ice and CO2, it's a bit worrying, and almost outside for temperature. There are several suggestions. Rudiman in 2005 thought we began to influence climate 100,000 years ago, domesticating animals and starting farming. Well, we did do both of those, I agree, but that's not necessarily when it started. And more interestingly, there are things called proto-weeds, weeds that plants will become weeds later, but they're not yet weeds. But they need ground disturbance to grow in new areas. And Sturr and his co-authors provide evidence of the origins of cultivation long before Neolithic farming, dating to around 23,000 years ago. Now we know the Earth's orbital path far into the future, so we can now, instead of forecasting the last 100,000 years, forecast the next 100,000 years to see what's going to happen. We're going to calculate scenarios, no human intervention. What does the model say it'll look like? Anthropogenic emissions of CO2 at 400 parts per million, a bit below where we are now, but not too far, and 560, which is RCP 8.5, which is the business as usual prediction that we'll end up at. We start the forecast 10,000 years ago to try and avoid the fact that it's already off course. So that's what it looks like. The dotted blue lines are our forecasts 100,000 years into the future, and they certainly look like episodes in the past quite happily, although we already know that we're lying outside these potential predictions. We're not anymore in a natural ice age, we're in an Anthropocene. And if we look at what happens at 400 parts per million and 560 parts per million, and this is quite complicated. I've shown you the graphs as to what they would look like in parts per million, but you have to do it in logs. The jumps are too big, and we then solve back from the logs to the levels. Then the least ice age volume is quickly underplayed. We almost end up with an ice-free world, which we've had in the past, but remember, it's killing species en route that matters. And then the peak ice age temperatures are way above. Antarctica will go up to about 20 degrees. Don't think there'll be much ice left there. We'll have a lot of flooding going around the planet, although that's only about 6 degrees for the planet as a whole, which is still going to boil a lot of places, and the whole of the tropics might become unlivable. Some of this is, of course, due to the Industrial Revolution, but I want to stress the Industrial Revolution, which did begin in Britain in the 19th century. The antecedents did lay 2 centuries earlier in the Islamic world's work and science and technology, medical knowledge evolving in Europe, but we were the first country to industrialize on a large scale, and it's had an enormous impact worldwide. There are startling consequences that nobody at the time could have imagined. Real income levels almost everywhere are 7 to 10-fold higher per capita. Many killer diseases have been tamed because we've got the income levels that we can work on science to look at them and find out what we can do about them. And longevity is approximately doubled relative to the 1700s around the world. So greenhouse gases were an unintended and potentially unnecessary consequence of of economic development. We could have had an almost totally electric world. And I want to stress that, because if we had, we wouldn't have had any of these problems, and there'd be no connection between GNP and climate, which many people assert is a nuisance. So the first continuous battery was Volta's voltaic pile in 1800, and unbelievably, Nicholson and Carlisle developed electrolysis. The electrolysis takes water and it splits it into air, which is oxygen, and fire, which is hydrogen. So water is actually made up of two of the components, not really a separate one at all. And they did that almost instantly in the way scientists in those days did. They passed electricity through everything, and then suddenly discovered when they passed it through water, they got some very interesting results. Electromagnetism was discovered in 1820, and the first electromagnetic rotation was created by Faraday, Davy, and Wollaston just 1 year later. I want you to note all these quick changes. 1926, the first high-efficiency water turbine by James Francis, and then 5 years after that, the first electric generator was invented by Michael Faraday, and that transforms the world. Almost all the lighting, the computers, everything electric here comes from electric generators of the kind Faraday developed. Practical refrigeration came 3 years later, right? Now, it had been invented and demonstrated in 1728 by William Cullen, but not using electricity. He showed that you could get artificial refrigeration. The first fuel cell, 4 years after that, by Sir William Grubb, and the first photovoltaic cell by Edmund Becquerel the next year. Then in 1852, Lord Kelvin proved the theory of heat pumps. How do you get a heat pump? Well, go and read Kelvin's article, he'll tell you. And the first operational heat pump by Rittinger is only just 5 years after that. And a year before it, Eunice Foote was the first person to demonstrate that CO2 is a greenhouse gas. It heated greatly in the sun, and air left on its own did not. Tyndall confirmed that 3 years later. Also, we're beginning to take interest in nature. Yosemite is placed under federal protection by Abraham Lincoln. Then the first UK electric hydro generator is a decent way of getting electricity was Sir William Armstrong, and the first commercial one just 12 years later, Grand Rapids, Michigan. First commercial photovoltaic solar panel by Charles Fritz 3 years after that, and the first wind turbine to generate electricity in 1887. We moved things once Tesla, he really was a man, but Nikola Tesla, that the car's named after. 1888 showed how to convert DC to AC, direct to alternating current, and that led instantly to the first electric street railway in Richmond, Virginia, which had a constant speed motor, regenerative braking powered by overhead wires. 1888, we're not even there in many cities today, right? We've gone backwards. 1880s, we've got the first electric cars with high capacity rechargeable batteries, just what we have today. And then Svante Arrhenius proved that atmospheric temperature changed proportional to the log of CO2. So we're there. It's all ready to have an electric world. Where did we go wrong? We've got solar panels, we've got wind turbines, we've got rechargeable electric cars, we've got electric trams, we've got absolutely everything to do it. We did not do it. There's a picture of a Bercy electric cab in 1897, well ahead of any other vehicles around at the time. And then Nansen ship Fram going to the Arctic in 1893 to 6 had a wind turbine on board which generated electricity for lights in the ship at night because they got stuck in the Arctic for 3 years. And people were very grateful to have not just dark all the time. And what went wrong was with steam trains, steamships, steam pumps driven by burning coal, all well established and a huge investment, and people are unwilling to move, but that's actually not crucial. What was crucial was there no nationwide electric grids to supply electricity. With a car, you can go from A to B and you hope to find a filling station somewhere near B, but you couldn't find any electricity near B unless something was supplying it, and that requires a grid. And the UK did not get its first nationwide standardized grid until 1926. And US buyers and motor manufacturers switched to internal combustion vehicles, which quickly outpeated electric cars because all the research went into that. So we missed out 120 years ago, sadly, and now we've got a worldwide serious problem. What's the UK doing? Well, this is a graph of UK CO2 emissions since 1860. Rose dramatically with coal, but notice most of that's exported. Britain's producing trains, rails, ships, etc. for the rest of the world at the time. Then the national grid gets created in it's a dummy for 1925. We reach peak 700 megatons of CO2 in the late 60s, and then we start dropping, and we drop very sharply after the Climate Change Act of 2008 and implementations of it in 2015, 2016. Now, everyone knows what happened during COVID, but over the period since 1995, when climate change began to be treated in Britain, GDP has risen by 48%, which is approximately 2% per annum, although it's tailing off at the moment, but not because of climate change. Amazingly, the amount of power we're using in Britain has been falling very dramatically over the period since 2000, because we're getting more and more efficient at using it. You know, your LEDs, your cars now go 50 miles to gallon rather than 20 miles to gallon like American cars. And then our coals come down, so that's got rid of the worst polluter. Oil dropped sharply after the first oil crisis. So hey ho, let's have a much higher price of oil and we might get rid of it even more. Natural gas came in when it was discovered in the North Sea, and then nuclear and renewables at the very bottom. And these are showing the energy for electricity in the next graph. And the efficiency is very marked. It's dropped by the use of the CO2 emissions per unit capital stock has dropped by 93% since 1860, which is a very dramatic increase in the efficient use of energy. There's many published proposals, and they all agree we can decarbonize electric generation by 2050, although this government wants to try and do that by 2030. I think it was wrong. Less so doing it reliably at scale. There's very little in the roles of nuclear, bioenergy with carbon capture and storage, BECCS, which I think is a disaster, and how to get electricity into the grid from vehicles. I mean, it also differs greatly in how we tackle the storage of variable renewable electricity, which is quite important, and in decarbonizing housing, construction, transport, industry, chemicals, agriculture, and waste. So we think there are very important gaps out there, which we hope to get dealt with. Now, a sensitive intervention point is when a system is near a critical or tipping point, so a small change triggers a much larger change that becomes essentially irreversible. In fact, the legally binding 2008 Climate Change Act is a lever that comes in at the right time, bans coal, changes the generation of electricity, and we immediately start getting a big drop in our CO2 emissions. But it also depends on technological developments. So here are our 5 steps summarized in case I run out of time, which looks increasingly likely. Expand green electricity using thermal, wind, solar, possibly nuclear, hydro tides and waves. We need a 4 to 8-fold increase in electricity. Now, total use of energy in Britain at the moment is 2,200 terawatt hours. Electricity is just 350. You might wonder why we don't need about 8-fold, definitely. And that is, electricity is vastly more efficient for running things than coal or oil. Coal is dreadful. It's very inefficient. Most of it's wasted, but so is oil. Feel the engine in your car. It's boiling hot. A lot of the energy they all went into heating the engine, not to driving you. So electric vehicles connected to a smart grid for short-run backup storage to balance variable renewable supply will greatly reduce the amount of energy we actually need, but more of it need to be electricity. Now, if we have lots of renewable supply, we'll get excess supply, we already have many times, so we can get low-cost hydrogen from intermittent surplus renewables and then turn some of that to liquid hydrogen, which is both medium storage and a high heat source for industry. And then finally, we can start making agriculture much more electricity-based, grinding basalt, making biochar, having underground invertible farms, and then catching biomethane-based electricity. So what can be done? First, eliminate coal, then eliminate oil, then eliminate natural gas. It's got to be done sequentially to get electricity generation, massive increase with linked electricity intelligent grids, and balancing in various ways. And I disagree with the government's policy because I think oil produces 30% more CO2 per kilowatt hour than methane. So producing electricity with natural gas to get rid of internal combustion cars is sensible. It's not stupid. It's something we ought to do. We need backup renewable electricity by safe, small, modular nuclear reactors because we just will not have enough steady supply with decent backup otherwise. And then technical issues are storage systems, economies of scale and SMRs. They also can use transuranic waste. We've got a serious problem getting rid of radiation in this planet. Well, you might be able to feed it through SMRs and greatly reduce it. And we could possibly have fusion appearing sometime before the end of the century. And we're running out of helium. It's the only natural thing we're running out of, and we can get that from fusion. Wind turbines and solar PVs coming in everywhere. High Wind Scotland showed the viability of floating wind turbines, easier to install and dismantle, but falling wind speeds might be a problem. We might use energy from waves and tides. Nuclear has cast a pall over its technology, but it's about 70% of electricity in France. And had the Japanese installed offshore wind turbines, which are immune to tsunamis and earthquakes, they could have maintained power at Fukushima Daiichi and not caused the problem that happened there. It's a very stupid mistake not to have an offshore generation of electricity to it, even though it was a very bad platform. The 2025 looks close, but already it's probably too low to stay below 2 degrees, but we can make a real effort. To do that, we have to get rid of internal combustion energy cars. We can do that in many ways. Then we get them connected to a grid, which give a very low cost investment to society for short-term electricity storage. You're plugged into an intelligent grid. They run out of electricity. They download it from your battery, and you get paid peak prices. And then when you recharge it, you're charged trough prices. So you can actually make income out of having your car when you're not using it connected to a grid. Now, cars have risen dramatically, as have the miles driven. At the very end, that's the COVID lockdown. But tenfold increases in distance driven despite more than doubling in real petrol prices. So carbon tax isn't very effective. If doubling it hardly stops you a tenfold increase. But it has led to much more efficient internal combustion engines, although EVs still win over time. Retrofitting old buildings is quite expensive, but it can be done. Heat pumps can heat entire villages. France has already got 3 million of them. We've got very few. We've shown it can be done by retrofitting a Glasgow tenement, but we can also raise fridge and freezer standards. And all electric houses, however, will need resilience. They will need their own separate storage. Many technical issues to look at. We can decarbonize construction. We've actually only just now, the last couple of years, discovered both that glulam is a fantastic material. What you think there is steel is actually glulam. It's wood laminated together and prefabricated, and we can get high insulated dwellings. And Roman concrete, the Pantheon's still standing 2,000 years later, and we've only now discovered how they made the concrete to do it. And then we can get liquid hydrogen for energy, and we can reduce CO2 emissions in agriculture by stopping deforestation and peat use, restoring wetlands, having mangroves. But basalt is where agriculture began in this planet. It began on the side of a defunct volcano because basalt's enormously effective, very fertile land around volcanoes. And so if you start replacing artificial fertilizers by basalt dust, it also absorbs CO2. And that will cut out 2 uses of CO2. Cut down cropland and environmental damage by using crop production, zero tillage, etc. And we need to improve agriculture. So in North Rawlinson, there's a breed of sheep that is forced to live off seaweed. It doesn't produce any methane because enterogenic methane only occurs when you've got methanogenic bacterial activity, and they can't have that with just having a seaweed diet. So we can do that. And recently in their science paper, which surprisingly was also commented on very favorably by Nature, and has already got 100,000 downloads in the 6 months since it was published, my team, together with a number of others, applied our break detection methodology to OECD's database to show that across all the last 2 decades, 41 countries, all 4 sectors, only 63 climate policy interventions out of 1,500 were identified as inducing major sectoral reductions. And they found the UK had reduced its UK electricity emissions by around 44% relative to not having those interventions. Anyway, I'm going to skip through implications of climate change. Atmosphere can be quickly changed now. Just let me go right through to our little the journals insist on these kind of stupid things now. So this is ours, the 5 sensitive intervention points. You can read around it. Thanks very much for listening.
Thank you, David, for that very interesting talk. We can take a few questions from the floor. Yeah, Nicholas.
So my question is on IAMs, integrated assessment models, which are largely used by policymakers. So it's been heavily criticized by Dexter and Weizmann.
And lots of other people.
Yeah, that it lacks some kind of scientific rigor, even though the coefficient estimates of the equations come from the IPCC. How do we get better IAMs? How do we improve it to so that we can incorporate the probabilities of catastrophic events and tail events and make it more scientifically robust?
When you've got an hour, we'll answer that.
Okay, right.
Obviously, you require methods like ours to model the breaks, because one of the reasons IAMs give completely stupid predictions is they're not allowing for change in the change. They're assuming the change is constant, but the change is changing. And unless they start modeling that, they'll never get near it. There's so many problems. But the chairman of our advisory board, Thomas Stern, has written a much more powerful paper criticizing IAMs than any of the other ones I've seen in the literature. If you want to go and read that and see why he thinks they're very wrong.
Okay, yeah, another one, like, is the government and is the private sector's pursuit of like the artificial intelligence arms race and being the king of data, is it counterproductive to all the environmental policy that governments are seeking to achieve?
Who knows? I mean, with artificial intelligence, you could actually run an intelligent grid, which humans would have difficulty doing. So there are ways in which you could see it being quite positive, but the amount of electricity that's being wasted in lots of activities of it is certainly counterproductive, as we don't have yet sufficient electricity for everything.
All right. Also, should we rethink how we look at a discount factor, which is largely determined by the Ramsey model, and how we look at the SCC, social cost of carbon? Should we
I answered that in a paper in 2010, saying that you should think of climate change as being in a car that's got no brakes and is running down a mountain and would drop off a cliff 2 miles down the road. Do you jump now, or do you stay in the car discounting the future?
Right.
That's my answer.
Right. Thank you. I'll look up your papers.
More questions from the floor? Go ahead.
First of all, Professor, thank you very much for the presentation. I wanted to ask, is there actually a deadline for change? Because some climate change activists are saying that we are far past that point, and all of the policies that we've already implemented, we've hurt the environment basically so much that we can't really stop it or change how it will be going in the future. Is there really a deadline for basically changes?
They have not produced a model that shows that. That's an assertion that they make, right? It's possible. I've said several times that we've been developing methods for detecting tipping points so we can quickly pick up if they're happening. And there are signs of various tipping points occurring in different parts of the planet. Off Brazil, they've discovered that the ocean conveyor belt has slowed down quite markedly, which would affect the Gulf Stream, and consequently, we might end up frozen rather than boiled. So there are possible things out there, but I have not seen yet reliable models that would say that we've passed achieving it. And most of the calculations of our carbon budget suggest there's a little bit to go, right? But there are many signs that the large models are not actually modeling what's happening. And they include the huge floods. They don't have that. The increases in the power of hurricanes, which they said wouldn't happen. they'd be broken up by the increasing winds. And most importantly, the number of heat bulbs, heat domes that have occurred in places that couldn't possibly have them according to the models, like over northern Canada, for example. And you could not have had that in an IPCC model. You couldn't have had the jump in sea level, sea surface temperature. That's again not something that can happen in an IPCC model. And in July 2 years ago, the North Sea rose by 4 degrees. The North Sea, right? Have you ever swum in it? It's freezing. Could you imagine it rising by 4 degrees? How did it get there? Where did the hot water come from? Right? Because it's not connected to the Gulf Stream, for example. So yeah, there's lots of things happening that's suggesting that the IPCC needs to start taking account of changes and changes in a way that we have recommended for about 20 years now, and which we apply in all our work.
Professor, according to you, we seem to have been quite efficient in Britain in reducing our energy consumption, but we only produce about 1% of the carbon dioxide pollution in the world. What about the other countries? We've just seen the Paris thing has been rubbished by America, and it's not even in. China's not even included in all this. So where are we going to go?
Yes, I have worked in the UK economy for more than 50 years. I understand how it works. I understand how economic behavior gets communicated to our climate behavior. I have not worked in China or India, right? I can read the literature on what's happening there, but I'm not there. We're showing methods and ways of approach, and from our SIPs, how you might approach even in China. In fact, one of my postdocs, Ryan Rafferty, has published a paper on how China could get much more rapidly to net zero using some of these SIPs to help it, because it's got the cheapest solar and the cheapest wind, and it's still got expensive coal, right? So it's biting off its nose to spite its face by creating a huge output of CO2 from an expensive product, and it's actually changing very rapidly. It could be one of the first countries to become more green than brown. I don't know about India, but India's made the same mistake. And you can see how it happens. You're the head of a region of a country. You've got a coal mine, you've got coal miners, and you're going to say, and you've got a power station that burns the coal. You're going to say, oh, we're going to stop doing this. And they need a Deng Xiaoping approach to things, where he looks at what can we get these people to do when they're not doing mining. Well, let's get them moved over to doing that, and then the mine will close. I know that. I can do nothing about politics in the USA. I mean, I can only say they're crazy. Their miles per gallon of car travel is almost exactly what it was in 1920. Britain, by having adopted standards, petrol pricing, etc., we get 50 miles to the gallon, not 20 miles to the gallon. And that's an enormous difference. And that's because they won't tax oil. And they have idiots like Trump saying, oh, we need more of it rather than less of it.
Are there any questions from on the web?
I don't see any.
Okay. I have a small question. All of these graphs have these spikes, and then there's somehow a reversion down, right? There's a sawtooth pattern to a lot of
which
them.
graphs?
Of temperatures, I don't know, right towards the beginning.
All right, towards the beginning.
I thought I saw them. No. Oh, yes, that kind of pattern, right?
Yeah. Yes. Well, these are.
I mean, even temperatures. There are periods. It's a very jagged picture. So, are you saying that now it'll keep going up? There will be no reversion back down again.
no, these are natural variations from orbital behavior of the planet,
Right.
right?
Right.
And that's what the orbitals have done. They've created this change in ice ages by this mechanism that Milankovitch spelt out, that you get a cooler summer, the ice doesn't melt and it builds up, but then you get a warmer period coming in, perhaps because the tilt is slightly
Yes.
different, and it goes away. Because remember, these are 1,000-year intervals
That's right.
in India. So although it looks spiky, if you took
Smooth it
a,
out,
a
yeah.
bit,
If you take a
bit of it and
longer
spread it
scale.
over just 100,000 years rather than 800,000
Yeah.
years, it would not look nearly so spiky. But yes, it seems to turn around very quickly, and that is surprising. It's some people have used business cycle models to say, "Ooh, it goes up quicker than it comes down," but we don't find there's some evidence of that, but we don't find that it's a systematic pattern. You get patterns where it goes up and
But
down.
So
in
you're
very
more
similar-
interested in looking at what happens once you've taken account of, I don't know, changing of the poles, the changing of.
Yeah,
all-
yeah, we
all-
take it.
and Given all that, what's going to happen if we don't?
Yes, well, given all that, we find that there is feedback between temperature and
I see,
ice, and ice and temperature
Yeah,
and CO2.
yeah.
So it's lagged, but it's 1,000-year lag because that's the level of the data. And that means it's a runaway system. So
Mm.
yes, it might not come back unless we do something about it.
Yeah.
Nature did something by making the Earth move closer or further from the sun.
But
at
it's
various
not-
times
that's
of
not
years,
going
and
to
that
be enough.
started- And that's not going to be enough because these are 1,000-year intervals, right? That things are taking much longer to happen than humanity's got time to think about. We haven't even got 100 years to think about this in India.
Mm-hmm. Yeah, indeed. That kind of doom-laden approach is probably
No, we
doom
can
laden.
do it. We
We
just
can do it.
aren't doing it. It's
And
not
it's-
that it's impossible. It's
And
that
it's
we're
not,
being stupid.
and we're going precisely the other direction in some parts of the world.
Yeah,
So,
yeah.
Alessandro, do you have a question? Oh, no. Okay. Very well. Thank you very much for coming. There is a small reception outside, so please do stay and talk to our speaker if you must have more questions to ask him. So we close by thanking David for a very informative and illuminating talk. But please do